Stochastical simulations are some of the most powerful methods in modern mathematics. For this, it can be useful to simulate arbitrary probability densities. The generalized Ziggurat-Method is a new method we propose that achieves this. In this talk, we will illustrate this by the beta distribution. First, all simulations are based on uniformly distributed pseudo-random numbers, which for the sake of this talk, we will just view as uniformly distributed. For an arbitrary distribution, we can compute a random variable via the quantile transformation using the inverse distribution function. For this talk, we want to simulate a beta distributed random variable. This can be done by using the acceptance rejection method, where we sample from one variable y and accept this value for specific cases in order to get a sample that is distributed like x. We want y to be easy to sample from in order to have this method be most efficient. Here we can see this can be imagined by sampling under the distribution function and accepting the values when they lie under the distribution we want to sample from. This can be achieved by using the test function gamma. We can prove that this method works for random variables x being absolutely continuous to y, so the test function exists and the variable turned out by the algorithm is distributed like x. For this lemma to hold, we need the theorem of Radon-Nikodym in order for the test function to exist. And then to transform the densities, we use the theorem of Fubini, which shows that the lemma holds. For a sigma finite reference measure to which both of these are absolutely continuous, we then have an enveloping condition which has to be held in order for the algorithm to work. From this now we can build the Ziggurat-Method, which was proposed for monotonically decreasing probability densities, mostly of scaling location families. In this method we use 2 to the k equal area reference measures to enclose the probability density by a step function. This can be seen here for the normal and exponential distribution. The components we use are the reference measures, the support point xi, the safe acceptance regions and the critical acceptance regions for which we use the test functions gamma. For the algorithm, we first proceed to multinomial sample from the reference measures because they are equal area and are binary in size. We can sample from a binary number to achieve this. This has the advantage that we can use the last digits of a uniformly distributed random variable as a binary number to sample from the index. Now we sample from eta e and the uniformly distributed random variable and accept if we are in the safe acceptance region or in the critical acceptance region we have the test function y being greater or equal to u. We can now generalize this method by, instead of using 2 to the k equal area reference measures, using arbitrary reference measures and having a multinomial preselection instead of the binary one. This allows for general distributions while keeping the high exception rejection efficiency of the Ziggurat-Method. Now we can look at the beta distribution. This is the conjugated prior of the binomial distribution, which means that the binomial distribution conditioned on the beta distribution is binomial distributed and vice versa. We can also simulate the beta distribution by 2 gamma distributed random variables with arbitrary scaling parameter rho. To simulate the beta distribution, we can use Masayas method, which uses this in order to make a Taylor expansion in the log of the transformed gamma density, which is then enveloped by the normal distribution. This is the method used in numpy.beta. Now we can propose a Ziggurat method for this, using a case distinction depending on the behavior at the boundaries of 0, 1. For this we look at the character of the beta distribution, which for parameters smaller than 0 gets a pole at the respective boundary. For the first case, we view both parameters to be smaller than 1. In this case, we need hyperbolas to enclose the boundary regions, and enclose the rest by step functions. For one parameter to be smaller than 1, we can use one hyperbola and step functions to envelop the density. And for both parameters to be greater than 1, the enveloping becomes trivial as the density is bounded. We can see here the advantage of the generalized Ziggurat method is that we can have densities which are no longer bounded because we can use unbounded reference densities. In order to optimize, we view the calling of different parameter combinations in every function call. This has the disadvantage that we cannot pre-compute the ziggurat and have to compute it in every step anew. We further do support point optimization, which in this case yields that at most one support per monotone region is ideal, which can be approximated by double logarithmic regression. We conclude with the runtime optimization by implementing in C and integrating into a precompiled Python module. Here we can see the runtimes of the different heuristics, which shows that an adapted method yields the best results. In the comparison of runtime speeds, we see that the Ziggurat method beats the NumPy method for generating better distributed random variables, while it cannot beat the self-implemented version of Masaya and only is on par for certain parameter choices. We can also view the correctness of this method, which, as the PP plots yield, show a convergence for large sample sizes, which confirms that the method samples correctly. As we have seen, the Ziggurat method allows flexible applications for arbitrary reference measures, even for densities which are unbounded in this case. This is a huge advantage compared to the normal Ziggurat method, which only can yield results for bounded cases. It is therefore feasible for the better distribution, whereas the support point choice is very difficult. This is why it can outperform standard methods only for certain parameter choices, but not in general. Because we do not have a scaling location family, the ziggurat has to be computed in every step, which is a huge pre-computation bound and only yields good results for small support choices.